In previous session, we have discussed about base tangent method, but we have also discussed limitations of base tangent method and vernier caliper methods, because if you look the equations, of base tangent and gear vernier caliper methods, all these equations they are depending on two parameters: number of teeth and module of gear. So if you are having gears with same module but number of teeth are different on those gears, then for each and every gear you need to do calculations separately and then you need to use that method. That is what the limitations of both the methods, base tangent method as well as gear tooth vernier caliper method. This limitation is overcome using constant Chord method. What is constant Chord method? See, first of all, let us try to understand this diagram. This is base circle. Then we have considered only one teeth of entire gear wheel, which is in symmetric mesh of rack. So this, if you consider these lines, this line 1 and this line 2, then these two lines, they are indicating flank of rack. So right now this gear teeth is in symmetric mesh of space between two racks, two flanks of rack. Clear? So right now we are considering engagement of gear against rack. So in this diagram, the teeth of rack are straight and inclined to center line by pressure angle. Means if you look here, this line is the flank of rack, this line is also flank of rack, and we are having space between these two flanks in rack, and there in that space this gear teeth is symmetrically meshed. Then as per the geometry of rack, this is the center line. This center line is indicating here, if you see, this is this O is indicating center of gear, involute gear, and if you consider this line, and this line stands for flank of rack. This line is considered as a rack form. See, here it is written, it's a rack form. So if you consider this angle, this much of angle between this center line and angle of this rack form or angle of flank of rack, then this angle is equals to pressure angle. This angle is equals to pressure angle. Now, one another important thing is, tooth thickness of rack at pitch line is equals to the arc tooth thickness of gear. If you see in this image, then this is pitch line of rack. This line D to E is representing pitch line of rack. Then as per the law of gearing between rack and gear, this pitch line of rack, that is tangent to pitch circle. This is pitch circle. If you consider this arc F to G, then that is pitch circle, segment of pitch circle. Then as per the law of gearing, pitch line of rack is tangent to pitch circle FG. And if you are considering symmetric mesh of gear teeth in the space between two profile of rack, then this point, the point where pitch line is tangent to pitch circle of gear, that is called as a pitch point. So here this capital P is pitch point. So as per the law of gearing, we can say pitch line length DE, sorry, here one mistake, it's not PD, it is DE, is equals to tooth thickness. Tooth thickness is F2G. This F2G, both are equal. So these two terms are important because these two terms, or these two conditions we'll use in our next derivation. Now, as per the name, constant chord method. If you look here, when you take 3 or 4 different gears with same module, with whatever the number of teeth present on those gears, if you mesh same module gears against the rack of same module, then always those always teeth of those gear, they make contact with rack at these 2 points A and B only, irrespective of total number of teeth on gear. Again I am repeating, if you consider any gears with whatever the number of teeth, but if those gears are having same module, and if those gears they mesh with rack with same module, then irrespective of number of teeth, always involute profiles of teeth, they make contact with involute profiles of rack at point A and B, and that's why line AB is called as a constant chord. Line AB is called as a constant chord. Now, as per this condition, if you look this condition tells us angle of rack profile with center line is pressure angle phi. So if this angle is phi, then if you consider one line from point A which is passing through pitch point P, and if I extend it, then that must be tangent to base circle. This line, if you look this line AP, then that becomes tangent to base circle. Okay, so this line make angle phi with the constant chord line AB. That is obvious as per this principle, because if this angle is phi, then this angle will also be phi. Okay, so AB is a constant chord length, and constant chord is present at certain depth D. Constant chord is present at certain depth D from top line. Okay, so this D and C stands for constant chord and D stands for constant chord depth. Then the C and D for any gears with same module remains constant. Means if you take 5 gears, all those 5 gears are having same module, but they are having different number of teeth. But if you consider those 5 gears with same module, they are meshing with rack, then value of C and D that remains constant. And that's why this is called as a constant chord method, because now we are going to measure length of constant chord at the depth of constant chord, which is similar to gear tooth vernier caliper method. But in case of gear tooth vernier caliper method, this depth and this thickness, chordal depth and chordal thickness, they were depending on total number of teeth present on gear width. And that's why this D and the chordal thickness and chordal depth, in case of gear tooth vernier caliper, they were variable because they are depending on number of teeth. But here the C and D, they are irrespective of number of teeth present on gear for same number of for same value of module. Okay, so now our target is to derive equation for C and D, and this method is again similar to gear tooth vernier caliper method that we will see later. But right now we try to now derive this C and D. So if you look in this diagram again, we are moving further. This is the equation for C and D. So these two equations we are going to derive. And if you see this equation, before moving further in the derivation, if you see this equation C and D, they are function of module. They are not function of total number of teeth present on gear, which was the case for gear tooth vernier caliper and base tangent method. But in case of constant chord method C and D, they are independent of number of teeth present on gear wheel. They are only depending on module. So if you are taking two gears with same module but different number of teeth, then value of C and D that remains constant. And that is the basic principle or basic crux of this theory. So that we will see now, derivation. So if you look here, this constant chord value C, in this diagram, if you see this AB line is constant chord. Now if you consider line AP, P is a pitch point, line AP is inclined to constant chord line AB at angle phi. Now if you consider line DE is what? It's a pitch line of rack which is passing through pitch point. So this line DE is parallel to line AB, means pitch line of rack is parallel to constant chord line. Both are parallel. So if this angle theta, if angle between line AC and AP is phi, then angle between line AP and DP is also phi. So this angle is also phi. Clear? This angle is also phi. Similarly, length of DP is equals to length of FP as per our second principle. If you look this second principle, length of PD is equals to length of PF. So PD is equals to PF. So PD is equals to PF. Now with this principle, let us begin derivation of C and D. So constant chord length C is equals to in this diagram AB. Now AB is equals to 2 times AC. AB is equals to 2 times AC. So that is our equation 1, relation 1. Now AC, if you look this triangle, we are having one right angle triangle, ACP. If you look here, CAP triangle with angle phi, if you apply cos phi principle, then AC is equals to AP cos phi. So that is our equation number 2. AC is equals to AP cos phi from triangle CAP. Now next I need to find out what is AP then. So to find AP, let's go for second triangle, which is DPA, triangle DPA, where DP is hypotenuse, AP is side, and here we have angle between line AP and DP is phi. Then now again I apply cos phi principle. Cos phi is equals to nearest side, that is AP, divided by hypotenuse DP. Then AP is equals to DP times cos phi. So that is our equation 3. AP is equals to DP times cos phi. Okay. Now DP is equals to, line DP is equals to arc FP. So that is what written as equation number 4. Line DP is equals to arc FP. Now what is FP actually? FP is half the gear tooth thickness actually. This FP is half the gear tooth thickness, because full gear tooth thickness is FPG. This F to G is the full gear tooth thickness, and full gear tooth thickness is equals to half of circular pitch. Full gear tooth thickness is equals to half of circular pitch, because circular pitch consider arc length for gear tooth thickness plus arc length for next space between two gear teeth. That's why FG is equals to half of circular pitch. Now circular pitch value is pi dp by n. If I do half of circular pitch, then I get FG. But here I want FP. Then I need to again take half of FG, and that's why FP is equals to 1/4 of circular pitch. So that is our equation number 5. Fp is equals to 1/4 of circular pitch. Now let us backtrack these equations. We know Fp in terms of dp and n. So let us put Fp value in equation 4. So put equation 5 in equation 4, then I get dp is equals to 1/4 because both are same. So dp is equals to Fp, that's why dp is equals to pi dp divided by 4n. Now if you see d by n, dp by n, dp is pitch circle diameter divided by n, then that is equals to module. So that's why we are replacing this. dp is equals to pi m by 4. That is equation 6. Now let us put equation 6 in equation 3. Value of dp in equation 3. Then I get ap. ap is equals to dp times cos phi. So ap is equals to pi m4 into cos phi. I got ap. So now let us put equation 7 value in equation 2. So equation 2, then AC is equals to AP times cos phi. So if I put value of AP, then I get AC is equals to pi m by 4 cos square phi. So we got AC. Now constant chord is equals to 2 times AC. We got AC, multiply by 2, then finally constant chord is equals to pi m by 2 cos square phi. So this relation will give us equation of constant chord length. So constant chord length is equals to pi m by 2 cos square phi. Now in this equation we are having only m, not n, capital N. So this equation is irrespective of number of teeth. See, the constant chord is function of only module. Now at how much depth this constant chord is present, that is d. So let us derive equation for small d, depth of constant chord. So depth of constant chord d is actually equals to, see, this P2 top line distance. P is a pitch point which is present on pitch circle. So pitch circles to top line distance, that is called as a module, that is called as an addendum. So P2 top line distance, that is called as an addendum. From addendum, if I subtract this CP distance, this CP, then I will get D. So that is the equation number 10, addendum minus CP. But you know, empirical relation, addendum is equals to module. So we are writing here m minus CP as equation number 10. Now let us find out what is the value of CP. Then again we'll use triangle CAP, but now we'll use sine principle. So sine phi is equals to CP divided by AP. So that is our next equation. So CP is equals to AP times sine phi. Equation number 11. Now AP, we know value of AP from equation 3. So in equation 3, AP is equals to dp cos phi. Sorry, not equation 3, AP is here. In equation number 7, AP is equals to pi m by 4 cos phi. So let us put value of 7 in equation number 11. Then we'll get CP is equals to pi m by 4 cos phi into this sine phi. Okay, so we got CP. So now let us call this as equation 12. Now put value of CP from 12 into equation number 10. Then D is equals to m minus pi m by 4 cos phi into sine phi. Again take m common, then we get finally this equation. So this equation is also depending upon module, not number of teeth. Total number of teeth present on gear wheel. So again, the constant chord depth is function of module only. So we got these equations. Now what we need to do, how to apply this method? So to apply this method, we know gear tooth vernier caliper method. Same gear tooth vernier caliper you need to use here, and you need to, for any module of gear, you need to solve this equation. So you get some D value and you get some constant chord value using equation 9 and equation and this final equation number 13. I have not given here equation number, but consider this as equation number 13. Then equation 9 is for constant chord length, and equation 13, that is for depth of constant chord. So just solve these two equations for any gear with its module and pressure angle value. Okay, so you get some theoretical value of D and theoretical value of C. Now this D is equivalent. Now I'm just going back, just remember this C and D. Now I'm going back to our gear tooth vernier caliper diagram. Okay, this is the gear tooth vernier caliper. So D is what? Same D is used here. So that constant chord depth will set on vernier B. Okay, value of constant chord depth will set on vernier B. And then after, if you arrange any teeth between jaws of horizontal vernier caliper E, then that would measure value of constant chord C. That would measure value of constant chord C. So I have theoretical value of constant chord using equation number 9, and practical value I have measured using this instrument. So actual value of constant chord thickness, constant chord length, and theoretical value of constant chord length. If they are having variation, that is again indirect indication that your gear tooth thickness is not correct. Now there will be a question in your mind: if gear tooth vernier caliper is measuring chordal depth, is measuring chordal thickness at chordal depth by using this arrangement, same arrangement we are using in constant chord method also. We are measuring, we are setting constant chord depth on vernier B, and using vernier E we are measuring here constant chord length. Then what is the difference between these two methods? That would be your question. Your question is genuine. But remember, for any module, now suppose if you take two gears with same module, but both are having different number of teeth present, then for both the gears, this equation of chordal depth and chordal thickness are different, because they are depending on M and N both. So that is the issue. Then for both the gears I need to set different value of D, because D is function of N also. But in case of constant chord method, D, depth of constant chord, is only function of M. Means now again if you take two gears with same module but different number of teeth, then value of D is same for both the gears, though they are having different number of teeth present, because constant chordal depth and constant chord thickness both are independent of number of teeth present on gear wheel. So you need to just make this instrument like a gauge. You know about gauge. What I need to do for particular module, I need to set constant chord depth on vernier B. Then after lock it. Don't allow it to adjust. Yeah, for particular module, I'll set value of constant chord depth on vernier B. Then after I permanently lock it. And then if I do measurement for any gear with same module, then I know length of constant chord remain same for for whatever the number of teeth, but if the module is same, then these two parameters, this D and C, remain same. So now I can make this gear tooth vernier caliper as a gauge for particular module. For particular module, set some constant chord depth on vernier B, and then after lock it permanently, and then only operate this vernier E for measurement of constant chord length. Okay, so in that way, constant chord method is more advantageous compared to gear tooth vernier caliper method, because in gear tooth vernier caliper method, if you take two gears with same module, but if number of teeth are different, then you need to again change vernier B setting. But if you are using constant chord method, and now if you have two different gears with different number of teeth, but if they are having same module, then constant chord depth remains same for both the gears. So I need not to change again and again value on vernier B. I need to every time just measure vernier E, value using vernier E. So the first limitation of gear tooth vernier caliper method, that caudal thickness is function of caudal depth. But now if you are using constant chord method, then that limitation is removed, because constant chord length is again independent of constant chord depth for same module of gears. Yeah. So in this way, constant chord method is more advantageous compared to gear tooth vernier caliper method. I hope funda is clear. If you have any doubt, then you can write your query to me. You can send me email, and we will be arranging a query solving session on Saturday. So at that time you can ask your queries. I will try to sort out your queries. Have a happy learning.